Good morning, everyone. On behalf of Pi Mathematics Association, I would like to welcome you all to the second day of uh, Ramanujan lecture series. So I hope you all enjoyed yesterday's sessions. So today also in a similar way, we have three online sessions given by three distinguished speakers. So before we start the session, I would like to give a brief introduction about our Pi Mathematics Association. So yesterday, our association member Shankar had given a detailed introduction. So now I will just brief it upon that. So Pi Mathematics Association was started in the year 2007 by Professor R. Sivaraman of DG Vaishnava College with the objective of removing the fear of mathematics among the students and general public. So since inception, our association has published several books, both in English and Tamil, to help the students to understand the complex concepts and learn the concepts easily. Our association has conducted several workshops, exhibitions, and seminars across educational institutions in Tamil Nadu to help the students to grasp the concepts easily so that they can, instead of memorizing, they can understand the concepts and they can learn it. Our association also has created multiple vinyl charts and models through which complex mathematical concepts can be demonstrated easily so that the students can visually understand the concepts. Apart from that, our association is also conducting internship program every year to equip the teachers with the advanced teaching methods so that it will be helpful for them when they are teaching the students. So every year we'll be conducting the lecture series and seminars in like a classroom mode. So because of the COVID situation, this year we have planned for an online sessions. So I welcome you all again to the second day of the Pi Mathematics Association Ramanujan lecture series. So today we have our distinguished speaker, Professor R. Thangadurai from Harish Chandra Research Institute to deliver the lecture. He is one of the very active number theorists in India, and he is also one of the famous number theorists in India. So we are pleased to announce that he is going to deliver our the first lecture for our association. So I now request Dr. R. Sivaraman, founder of Pi Mathematics Association, to formally introduce our distinguished speaker to the audience. Sivaraman sir.
So, good morning to all. Welcome to the second day lecture program of Pi Mathematics Association. We are very grateful to Professor R. Thangadurai for accepting this our request to provide a lecture today. Professor Thangadurai is not new to our association. He has been coming. He has already came to our association before, and with our request, provided he has provided some one lecture to our institution, DG Vaishnava College. I think that is around June of this year, June or July. I hope it is on July of this year. And Professor Thangadurai, like all other speakers of yesterday, was in spite of being achieving so much, he was very simple and very humble. Also, he could not even give his profile to us. Gave that work to us. So maybe the problem is if you could miss something, you have to apologize us because we don't know what is the key issue in your achievement. But anyway, achievements are secondary. Our work is primary. So for people like us. So please pardon me if I could miss something vital in your introducing. Um, so Professor Thangadurai has been working as Professor H category at Harish Chandra Research Institute, Allahabad, India. And he has been from Palankote. He studied his post graduation from Tirunelveli district, Palankote. And when I saw his credential, he also have written that he has done his MA. So he is both equally well versed in arts also. So I hope uh, that's an extra credential. And apart from being a mathematician, he has also been involved in many lectures and programs. I had visited a couple of occasions in other places when we both were giving lectures at that place. So he was very kind to give lectures to any place that he was called of. And his important contribution, according to me, is to edit SS Pillai's work. SS Pillai, remember, is one of renowned mathematician after Ramanujan's time. He was a great number theorist since Ramanujan. And so collecting and editing SS Pillai's work was, according to me, was Thangudurai's big work. And I hope, I believe that it was released in the uh, 2010 International Congress of Mathematicians Congress. I got a volume, and I went through only few pages, and I kept it safely. But anyway, I was following both Thangadurai's work as well as SS Pillai's work. So if you at all you have any doubt or clarification regarding works of SS Pillai, I think Professor Thangadurai is the best person to consult with, because he has been working on his work. And he has also written few other. He has edited one conference proceedings in number theory, and he has written two good books that is on transcendental number theory, pillars of transcendental number theory, and I hope he is also one among them. I don't know, and that was published by Springer Publications, one of a very famous publisher, and he has also edited several books and conference proceedings, and he has written 11 expository articles, more than 50 excellent research papers. I hope when I asked him, he said around 57, if I remember. And 57 is you jokingly called Grothentic prime. So anyway, so we are very glad that the professor has come to us here to give his first lecture among us. And wasting no more time, I leave the stage to him. Thank you, sir.
Okay. Will share it. It's visible, no? Audible.
Yes,
Hello?
sir. Yes, sir. It's audible, sir.
Okay. So I'm thankful for the nice introduction, and I'm very thankful to Pi Association for giving me opportunity to speak on the occasion of birth celebration and birth anniversary celebration of Ramanujan. My topic of lecture today is 3 by 3 magic squares and arithmetic progression in rational points on elliptic curves. So I chose this magic square just because Ramanujan is always fascinated to magic squares when he was a school kid onwards. I mean, okay, but the point is this work will be, I mean, it was done after, in this century, in some sense, whatever I'm going to present. I'm going to give connection to magic square to ellipticals. Okay, so first we will start with Ramanujan. This is a well-known picture at Trinity College. So from his writing 5 by 5 magic square, Ramanujan's writing, he kind of parameterized 5 by 5 like this. Okay, so the Ramanujan work on magic squares are in the notebooks of Ramanujan, Srinivasa Ramanujan, volume 1 as well as volume 2. I mean, the references Tata Institute for publication in 1957. The another one is Ramanujan's notebook part 1 by Bruce Burnt. The original chapter of chapter 1 probably is found in Ramanujan early school days. Okay, and therefore much earlier than the remainder of this book, notebooks. These are the kind of starting of Ramanujan magic squares, but we are going to get into 3 by 3 only. We are going to focus on 3 by 3 magic square, and we will link it to elliptic curves. So I'll start with the definition of magic square. 3 by 3 magic square, it's kind of array. 3 by 3 array consists of integers like matrix Aij, 3 by 3 matrix. Here, magic square means sum of the rows, sum of the columns, sum of the diagonal, and sum of the counter diagonals. all are same values. Okay, so then we call it magic square. Okay, so this is the generic 3x3 magic square definition. Okay, so we want to understand the entries, how one can create this magic square. Using this property, we can easily create. First of all, you sum all the entries, distinct entries of this magic square. Then how many we will get? 3 S we will get. Okay, so note that sum of all the entries of S is 3S. If okay, and if we add all the entries of middle column and middle row and the diagonal and counter diagonal, then we get how many? We get 4S. Okay, but the point is some of all the entries will be there, plus the middle term A22 that will be appearing 4 times, but one is inside one particular thing. Therefore 3S plus 3A22. Therefore 4S equal to 3S plus 3A22. So it means A22, the middle term must be S by 3. So now by putting U as a change a variable, U equal to A11 by S by 3, V equal to A31 by S by 3 minus S by 3. Then we can parameterize the magic square for a given ABC integers as follows. Okay, so this is the way we can parameterize the magic square. So given you start with any arbitrary ABC integers and you fill it up, this is going to be magic square. Okay, this is 3 by 3. 3 by 3 is slightly simpler, but what we are interested is we want to link it to some theory so that some problem can be solved in different way, theoretically, in some sense. Okay, in this parameterization, if you notice, if we kind of enumerate this entries in different way, this way. So A minus B minus C, A minus B, A minus B plus C. This is an arithmetic progression with common difference C. First row, second row, third row, all rows are arithmetic progression with common difference C. All columns are arithmetic progression with common difference B. Okay, so therefore from a magic square, on the parameterization of magic square, we can come to 3 arithmetic progressions having same common difference, and columns also this arithmetic progression with same common difference B. Okay, so conversely, if we are given 3 such arithmetic progressions, then we can construct the magic square just by putting the right places. Okay, so for a given ABC, and if we have this 3 arithmetic progressions, then we can construct a magic square, 3 by 3 magic square. So therefore it is we can easily cook up. Okay, the main problem is here what we are going to talk is something slightly different. Instead of the entries are all in any integer, instead of that we ask for a specific set of integers. The entries should come from a specific set of integers. Okay, what is that question? Question is, all the entries are perfect square. Suppose if we insist all the entries should be perfect square, and we want to construct 3 by 3 magic square. Okay, so can we do that? Yes, we can do that. Was simple example: 5 square, 1 square, 7 square. You just permute, you get 1. Okay, using this example, we can parameterize also this particular solution as this way. For a given pair m comma n integers, we can parameterize this. This will be a magic square. Okay, with each entry is a perfect square. Only drawback is in this one entry, I mean entries are repeated. Okay, not all distinct. In 70, Martin Gardner posed the following problem. What problem? Can we get 3 by 3 magic square of squares whose entries are distinct completely? The previous examples showed that the entries are repeated. So he posed whether we can construct with the distinct entries, we can construct 3 by 3 magic square of squares. Okay, then he offered $100 for an example of such a magic square or a proof of non-existence of such a square. Okay, so that time, nowadays Current Institute is giving $1 million questions, but that time only Paul Redash used to give a problem as well as the prize money kind of. He also has done, but $100. He the prize money they increase according to the level of the difficulty of the problem maybe, but whatever they have. Okay, so just for a fun, he has given. Okay, so we want to kind of whether we can construct or we can prove the non-existence of such a magic square of squares. Okay, with the distinct entries. So from the parameterization of 3 by 3 magic square, when all the entries will be distinct. Okay, so if all the entries are first of all squares, and when all the entries will be distinct, okay, we can just check this condition precisely when this condition happens. Okay, so either B equal to C, or B equal to plus minus C, or B equal to 2 plus minus 2C, or 2B equal to kind of plus minus C. Okay, this is the kind of condition. We take always B, C non-zero integers. So this is the kind of condition. In this condition only precisely when this all going to be distinct entries going to come. Okay, so that from the observation, so it's if we want to create 3 by 3 magic square with the distinct entries as well as all are perfect squares, we want to create 3-term AP among squares satisfying this particular condition. Okay, so therefore it means first we want to study among squares 3-term AP arithmetic progression. So what kind of property it is there? So first we will get into the study of arithmetic progressions of 3 squares. Okay, so let us enumerate first 10 perfect squares, 1, 4, 9, 16, etc. Among this, we notice that 1, 25, 49. These are all perfect squares, and this is forms a 3-term AP with the common difference 24. Okay, so note that 1, 25, 49 are in arithmetic progression with common difference 24. So further one can keep searching. One can get 289, 625, 961 is an AP. It forms an AP with common difference 336. Similarly, with the common difference 840, we can get 3 integers, perfect squares. Okay, so we write generically, suppose if A square, B square, C square are 3-term AP, then B square minus A square is equal to C square minus B square. That this is if and only if A square plus C square equal to 2 times B square. Since B is non-zero, since we are all looking for non-zero integers solution, so we can divide by it, and then we see that A by B whole square plus C by B whole square equal to 2. This means finding all 3-term arithmetic progression of squares in integers is essentially equivalent to finding all rational solutions of the circle x square plus y square equal to 2. Okay, also so once we are in this we can parameterize again any solution of rational solution of circle. We can parameterize. I may not give the proof, but it's a simple proof only. The points, any rational point on this circle other than 1, minus 1, this is like a point at infinity, described by this formula for any given integer m. We can write down a and x and y, this quotient of in terms of m, we get one solution. Okay, this we can parameterize, one parametric family. This is okay. So it means finding 3-term AP amongst 3 squares, it is kind of finding rational solution of a circle, of this particular circle, x square plus y square equal to 2. Okay. So suppose prescribed common difference is given. Suppose two arithmetic progressions are given with the same common difference. Then what is the link? That one has to understand, because in our magic square construction, we need three term AP with same common difference. Therefore, in order to solve that, we better understand arithmetic progressions of three squares with the prescribed common difference. Okay, so note that 1, 25, 49 are squares in AP with common difference 24. Similarly, one can check this rational squares also forms an AP with common difference 24. Okay, it's a kind of computation. Question: how many rational squares are there which form three-term AP with common difference 24, or in general for a given rational number D or integer D non-zero as a common difference? How many three terms AP we can construct, okay, in rational squares? Okay, so this theorem says, okay, so D is given rational number, then the triple of rational numbers A, B, C whose squares are an arithmetic progression with common difference D. This set, so you collect all those A, B, C tuples. These are all perfect squares, and they form an arithmetic progression. Squares forms an arithmetic progression of with common difference D. This set is bijective. Is bijection with another set of solutions m comma n, rational solutions m comma n, satisfying this equation d n square equal to m cube minus m. Okay, d n square equal to m cube minus m. How given a ABC, we can construct C minus B by A minus B, and this particular point, this point will satisfy the equation dx square equal to y cube minus y, kind of. Okay, given a solution m comma n of that equation, then we can construct three tuples of this of this kind, which whose perfect square whose squares forms a three-term AP with a common difference D. Okay, this is a bijective correspondence. These two sets are bijective correspondence. That's what this theorem says. Okay, this better reference for this is article of Conrad. I have given a reference for this. You can able to get it's internet notes. He writes. I have taken from his article only this particular theorem. He gives a proof of this. Okay, so prescribed common difference, if we collect all those ABC, then we can come to a kind of rational solution to some equation. Okay, so we are kind of trying to pass from here to there to here. So we are trying to understand this set of rational solutions of particular equation type. Okay, in the above result, when we put ABC equal to 1, 5, 7, then m comma n is minus 1 by 2 and 1 by 8, which satisfies 24m square equal to m cube minus m. So using the above result, we can get all triples ABC of rational numbers whose squares are in AP with a common difference D, kind of. Okay, these are all very theoretically going on. Okay, so that equation somehow d n square equal to m cube minus m, we transform this equation into different familiar thing, kind of thing. Okay, how we transform? Just we apply a transformation m comma n, you send it to dm comma d square m. Then any dm comma d square n, that you send it to kind of x comma y goes to x by d comma y by d square. Then what we are doing is a kind of rational transformation we are applying to get the equation, this m comma n is same as the rational solution x comma y, satisfying the equation y square equal to x cube minus d square x. Okay, if one understands the rational, I mean elliptic curves, this is the way we transform any given equation to elliptic curve equation. It's a Weierstrass form. Okay, it's a rational transformations. Okay, so in this process, what we are getting is this. I mean, same thing only, but by this transformation, we transform the bijection into different way. That's all. So for a rational number D, given rational number D, non-zero, the triple of rational numbers A, B, C, whose squares form AP with common difference D, are in bijection with the rational solution x comma y of the equation y square equal to x cube minus d square x with y non-zero. Okay, so this correspondence goes this way. Given a 3 tuple, how we come to the rational solution of this equation, from the rational solution of this equation to 3 tuple, how we are coming. Okay, from that previous theorem only, this is just using this transformation, we get this. Okay, now we enter another kind of introduction. A positive integer n that occurs as a common difference of an arithmetic progression of 3 rational squares. Okay, it occurs as a rational. It occurs as the common difference of an arithmetic progression of 3 rational squares is called congruent number. This is the definition of congruent number. Let us see the example. So 24 is a congruent number just because it is a common difference of 1, 25, 20, 49. And we divide by 4 because 4 is a square. When we divide by 4, then 1 by 4, 25 by 4 to 49 by 4. This is a square, perfect square, and the common difference is 6. Therefore, 6 is a congruent number. For 7 is a congruent number coming from this particular 3 rational number squares. And for 5, we can take this particular rational number squares. Okay. And 1 is not a congruent number just because there is no arithmetic progression of 3 rational squares whose common difference is 1. Equivalently, from that previous theorem, what we see is that we can say that the equation y square equal to x cube minus x has no rational solutions with y non-zero. Okay, similarly, one can prove that among the first 10 natural numbers, 5, 6, 7, that whatever we have seen, 5, 6, 7 are the only congruent numbers among the first 10 natural numbers. Okay, so we are kind of interested in this kind of equation, y square equal to x cube minus d square x. Okay, so let us look at the cubic equation. Here instead of d I have put n. So x cube minus n square x, this can be factorized this way, x into x minus n, x plus n. So since n is a positive integer, then these are all distinct. Therefore, the discriminant of the cubic polynomial is non-zero. Then this curve, actually this curve, we call it elliptic curve. Okay, whenever the discriminant of the cubic polynomial is non-zero over cube, then this curve we call it elliptic curve. Okay, the curve means set of rational points in the sense x comma y. So you collect all those x comma little y, so satisfying this equation. That is a kind of curve. We can plot it, and over C we can plot it, and then over C we can plot it, and then we call it, this is an elliptic curve. Whenever the cubic polynomial, right hand side, the cubic polynomial is discriminant is non-zero. Okay, so we will just see here k is a number field in the sense of finite extension, but we can take k equal to q itself. Here q is a rational field. E is an elliptic curve. Elliptic curve means it satisfies looks like this, y square equal to x cube plus a capital A x plus b, where a and b are lying inside q, rational numbers we can take. Any solution for this curve is a kind of point on that curve, E. Okay, so here we say that E is an elliptic curve. It means that cubic right hand side cubic equation in X is whose discriminant is non-zero. Therefore, we call it an elliptic curve. That's the condition. Okay, so we collect all those points X comma Y. Here I have written in general where X comma Y coming from K, and satisfying this equation. Here O is kind of origin identity element here. Okay, so satisfying means it when we plug little x little y on the equation, then it really satisfies. Okay, these are all called rational points. Here K rational points, otherwise Q rational points. In our case, Q rational points we are looking at rational. Okay, so why we are looking at this particular set. This we are going to give a group structure to this particular set. It's like 2 points you can add, you can kind of add. This addition is not the usual addition, it's coming from geometry. Okay, so the geometry is I'm trying to describe in the one picture. So since the right hand side is a cubic equation, either it has one real root or three real roots. Okay, so here I have taken, suppose this cubic equation has one real root, then the curve looks like see x-axis, y-axis I have not put, but the point is this curvy one, the straight lines, you forget about the straight lines, the rest of the curve looks like elliptic curve. This is the way we plot in real plane. Okay, so over real we have taken a plot it. Okay, in R2 we have plotted. So only once it cuts the x-axis, it means only one real root. If it has three real roots, then 3 times it cuts the x-axis, this cubic curve. Okay, so and y square, if you look at it, this is symmetry with respect to x-axis, and I mean symmetry, it is completely. Okay, so therefore how we are going to kind of define a operation, we call it plus operation. It's addition. It's not really usual addition, it's a different addition. You take 2 points on the curve, that's P and Q. We have taken 2 points on the curve. We look at the line joining P and Q, going through, you take a line going through P and Q. Really we can find a equation. Okay, and we are okay, so this line has to meet the curve once more. Why? Because line is y equal to mx plus c. Okay, then we are putting y equal to, I mean y square, instead of y, this mx plus c whole square equal to, we are kind of cubic, we are plugging it and checking the points. There are 3 points are there in x. Okay, 3 points are there. It means it has to cut one more point. Already the point P and Q has come, and one more point it will cut. That P star Q, that's what it is defined. Now what you do is you take the reflection with respect to x-axis. That is P. That is the point, the PQ. Okay, P plus Q. This is P star Q. P star Q is nothing but the third point where the line cuts the curve. Okay, then we take the reflection of the point, that is we call it P plus Q. This is the addition law. Whatever the geometric way we have described, everything can be put into a kind of, we can find the x coordinate and y coordinate of P plus Q from the x coordinate and y coordinate of P and Q. We can write down the formula. I am not doing it here. Just this is the kind of way of putting a group, I mean binary operation, and with respect to this binary operation, this becomes a group. Okay, so the identity element is kind of O. O is a kind of point at infinity. That's the way we say it is just above the curve, kind of point at infinity. So vertically upwards. Okay, that O lies. Okay, so this set is now it is a group. It forms a group, and you see because geometric way it is defined, P plus Q and Q plus P all the same. It's a abelian clearly, because anyway either you draw a line from Q to P, it is going to be the same, and the same Q star P also going to be same. Okay, so therefore it is abelian by the way we explain the operation. Model Whale, he proved that this is a finitely generated abelian group. Means only finitely many elements are needed inside. We can pick up P1, P2, P3, PR, some R points, which generate every other points can be obtained from these R points. Okay, so that means we can write the group isomorphic to T. T is a finite group. Is direct sum Z power R. Okay, Z power R, free group of rank R. Okay, this R is the rank of that elliptic curve we are going to say. This is what elliptic curve means. So we look at the equation y square equal to x cube plus ax plus b, where a and b lies inside that field k, or here it is q. And the condition, when we say it is elliptic curve, it means that the cubic right hand side cubic equation whose discriminant is non-zero over k, it should be non-zero. Then only then we call it an elliptic curve. Then we look at all the rational points on that elliptic curve, and it forms a group. It is a finitely generated abelian group, and therefore by the structure theorem, we know that any finitely generated abelian group will look like this only. A finite group direct sum the free part, the torsion part and free part. Okay, this is where R is the rank of the elliptic curve. Okay, so here we are interested in one particular type of elliptic curve, which is congruent number elliptic curve. That's what we are going to call. For a given natural number n, En is nothing but y square equal to x cube minus n square x. So already we have seen that the cubic, once given positive integer n, then the cubic curve has discriminant, all distinct roots, therefore discriminant is non-zero, therefore it forms an elliptic curve. We call it congruent number elliptic curve. So here, therefore by the model Whale theorem, we know it's isomorphic to T direct sum or Z power R. Okay, free part and the finite part. First, we understand what is the finite part. Finite part is finite group means every element has finite order. Here in Z power R, every element has infinite order. Okay, so the we can find out this is tunnels. No, this is okay. Okay, so one can compute this. The only finite order rational points on En are either 0, 0, n0, minus n comma 0, and the identity. Identity is the point at infinity. Okay, these are the 4 points of 4 points. This T is nothing but consisting of this 4 element group. This is each one is of order 2. Okay. Hence, combining this information, what we can conclude in our problem, suppose if the rational number n is the common difference for a 3-term AP of rational squares, then it is the common difference for infinitely many APs. Okay, why it is? For a proof, okay, let us see. Suppose n is the common difference for a 3-term AP. Okay, this means this 3-term AP rational squares leads to a rational point on En by the correspondence. Okay, we already saw this set, and it has a bijection. So we come to this Enq. We will come to a rational point on Enq. Enq, this rational point, this point has to have infinite order by the above assertion. Why? Because okay, this is okay. Okay, yeah, because our in that bijection itself, it is clear that this will be of not of this type. Therefore, it is infinite order. Once it is an infinite order point, then you take suppose P is such a point. See, P is such a point. P plus P you take, that is also inside Enq. From P plus P, that is nothing but 2P. 2p, this 2p is a rational point, this inside E and Q, this will lead to another 3-term AP by that bijection. Okay, so once you get 2p, then 4p you can take, 2p plus 2p. Again, this is inside this is never going to be identity, because it's all its p is of infinite order. Therefore you can keep blowing it up like this, repeated squaring, we can get infinitely many 3-term AP of rational squares with the same common difference. This same common difference coming from that bijection. Okay, whatever rational point here will give a 3-term AP with a common difference n. That is what E and Q does. Okay, from the bijection. Okay, so now we have to come back to our problem. So what we have so far done, so first we parameterize the magic square, 3x3 magic square. From that parameterization, we found that we have to, if we want to construct magic square, 3x3 magic square, we have to construct 3-term AP, 3-term AP. Okay, so since we want all the entries to be squares, therefore we want to construct 3-term AP among perfect squares. Okay, so therefore we studied what is 3-term AP among squares, and then which is related to some congruent number elliptic curve. Now we go back to our original problem of constructing magic square. Okay, so we are back to magic squares of squares, magic square of squares. Okay, if a square, b square, c square form a 3-term AP, then by taking x equal to a plus c by 2, y equal to c minus a by 2, and z equal to b, we see that x square plus y square equal to z square. Okay, from 3-term AP we construct a Pythagorean triple. Okay, conversely, every Pythagorean triple x, y, z generate a 3-term AP of squares by taking a equal to x square minus y, x minus y, b equal to z, and c equal to x plus y. Okay, so this is 3-term AP among squares is this set, this particular ABC corresponds to a Pythagorean triple x, y, z. Okay, and conversely also. First observation, 2 AP of squares of length 3 have same common difference of terms if and only if the corresponding Pythagorean triple rectangle triangle, corresponding Pythagorean right angle triangles have same area. Okay, that's so why. Suppose a1 square, b1 square, c1 square, and a2 square, b2 square, and c2 square are 3-term AP of AP having same common difference, and the corresponding with that bijection, we corresponding Pythagorean triples x1 y1 z1, x2 y2 z2, like this. Since what is given? Given is these two are. Oh, so by the correspondence, okay, by the bijection, we know xi is this, yi's are this, etc. Okay, since the common difference are same for these two progressions, we have b1 square minus a1 square equal to c1 square minus b1 square. Similarly, which is equal to b2 square minus a2 square equal to c2 square minus b2 square. Okay, this is what the first these two progressions have same common difference. So once we assume same common difference, we want to prove that the area is same. Area means x1 y1 by 2 equal to x2 y2 by 2. That's what we want to prove. Just computation. x1 y1, if you want to compute by the formula, by the bijection, x1 we know a1 plus b c1 by 2, y1 is c1 minus a1 by 2. Therefore, this product is same as this, c1 square minus a1 square by 4. Just introduce b square, subtract, add and subtract, then both are same, c1 square minus b1 square plus b1 square minus a1 square. Both difference are same. Therefore, it is that is this will become this middle term. This b1 square minus a1 square is same as b2 square minus a2 square. Therefore, the next two things are equal. So therefore, the last one is equal. Okay. So by just a computation, we can get the same area. Similarly, if the Pythagorean true triangles, right angle triangles are have same area, which leads to two arithmetic progression, 3-term arithmetic progression of same common difference. Just a computation. Okay. So this observation says, if we take two arithmetic progressions of squares of length 3 with same common difference, this is same as saying we will get two Pythagorean right angle triangles have same area. Okay. If n is the common difference of 3-term AP of squares, say a square, b square, c square, then the area of the right angle triangle is, we can just compute, this is n by 4. Suppose if any given positive integer n bigger than 1, we can write it as a square part and square free part. R is the square free part. If x, y, z is a Pythagorean triple such that the area is R, the square free part, then by just multiplying the Sx, Sy, Sz, this is also Pythagorean triple such that the area is S square R, which is nothing but n. So because of this, it's enough to assume n is a square free integer. Okay. So this observation just we have written just to reduce that. Okay, we don't need to consider all the positive integer. It is enough to consider only square free integer. Now we give a link of the above observation with a congruent number. Okay. Let n be a square free positive integer. X, capital X, capital Y, capital Z, and little x are rational numbers, with the condition that a capital X is bigger than, less than Y, less than Z. Then we can get a one-to-one correspondence, bijective correspondence between the right angle triangles of with legs x, capital X, capital Y, hypotenuse Z, and area little m. With this set and the rational number x, for which x minus n, x plus m, or each one are square of a rational number. Okay, already this is an arithmetic progression. Each term is a square. So 3-term AP of squares of rational numbers, that and the right angle triangle, there is a bijection. Okay, here the common difference is n clearly. Okay. So how this bijection happens? So given a XYZ pair, triple XYZ, we want to construct little x. Little x is z square by 4, because z square is already linked with the x square plus y square already. Okay. So little x is given, then we can construct capital X to be square root of x plus little n minus square root of little x minus n. Okay, similarly y and z we can construct. With this correspondence, what we can get is the right angle triangle with the given area n and rational numbers satisfying this 3-term AP squares. Okay. In particular, if n is a congruent number, if and only if there exists x rational number such that x minus n, x plus n are squares in rational numbers. Okay. So this means this n is nothing but the area of that triangle, right angle triangle. Okay. Okay. So from here we manipulate something to come to our real problem, where we started with Martin Gardner's problem. We want to lead to, we are trying to do all these jugglings just to give a link to a theory of Martin Gardner's question, so that we can able to answer, hopefully we can able to answer his question. Okay, that's why we are doing all this juggling. given a x, y, z, which are sides of the right angle triangle with area n, then we have x square plus y square equal to z square, and xy by 2 is n. Therefore, we create this equation x plus or minus y whole square is nothing but z square plus or minus 4n, which is same as, we can modify to this, okay, equation 2. If we multiply these two together, in the sense we x plus y by 2 whole square, x minus y by 2 whole square, if we multiply these two together, we get this equation. Okay, so we write instead of this, we are going to write just putting u equal to z by 2, okay, and v equal to x square minus y square by 4. What we get is u power 4 minus n square equal to v power 4. Okay, so u and v are rational solutions of this equation. Okay, so multiplying by u square once again, we obtain the following equation, u power 6. So we are just multiplying this equation, u power 4 minus n square equal to v power 4. Okay, we get u power 6 minus u square n square equal to uv whole square. Okay, uv whole square. Okay, this whole square, this is square, v square, it is not v power 4. Okay, uv whole square. Okay, so now we are in this equation. Okay, once more, by putting transformation, y equal to u times v and x equal to u square, what we get is y square equal to x cube minus n square x. Okay, so we started with what? We started with a right angle triangle with whose area is n. Okay, that's the way we started. We end up in kind of rational point on this congruent number elliptic curve. With you see, you note that in this correspondence, x is like perfect square in rational number, and the denominator is divisible by 2. Okay, that's important here to note. Thus, given a right angle triangle with the rational sides x, y, z and area n, we obtain a point x comma y in the xy plane having rational coordinates and lie on this curve. What about the converse? Converse, it means given a curve, given any rational point on this curve, can we get a right angle triangle with this area n? Okay, that is not true, just because already we noted that x is little x is really a perfect square in rational, x itself perfect square in rational, and whose denominator is 2. Okay, in general solution may not have such thing. Therefore, it is this converse is not true. But okay, that's what I have explained. X is nothing but y square. Y square is nothing but inside positive rational square. It is okay. So, and the denominator is divisible by 2. So, by putting all this information, we observe the following. So, let x comma y be a point on the rational with rational coordinates on the curve y square equal to x cube minus n square x. Suppose x satisfies the following two conditions. It is a square of a rational number. Suppose x is a square of a rational number and its denominator is even. Then there exists, one can cook up a right angle triangle with rational sides whose area is n, which corresponds to x under the correspondence of whatever we said. Okay, previously we saw the bijection right angle triangle to x rational. Okay, so therefore what we need is, we need to understand this set. Yes, S is nothing but, again the same notation, yes. Okay, set of all x comma y inside q cross q, such that y square, little y square equal to x cube minus n square x, with x is perfect square in rational and 2 divides the denominator of x. This is the set we want to understand, because this is the set it is giving back our correct right angle triangle, because right angle triangle is connected with the congruent number. Okay, so therefore this is the set really we are interested in order to solve, in order to answer the question of Gardiner. Okay, in this group E and Q, in this elliptic curve group, if you want to understand this, okay, it is enough to understand a subgroup of the form 2 times E and Q. What is this 2 times E and Q? E and Q is you pick any element P inside E and Q. P will look like a Q plus Q kind of type. Is 2 times, in the sense the same thing is added up twice. Every element of in a particular group 2 and Q, it looks like there exists element Q such that P equal to Q plus Q. This plus is the elliptic curve addition law. Okay, this is the kind of, we have to understand this particular subgroup. This subgroup has no finite order, just because already we have seen any finite order is only inside T. The T has only 4 elements, each one is of order 2. Once I multiply by 2, everything to identity. Therefore, whatever is non-identity element is there, everything will be of infinite order. Okay, if this is not equal to identity, this subgroup is just a singleton identity, then any element, non-trivial element, is going to be infinite order. That's the observation in this. Okay, if you pick any point in this, okay, and this point will be like Q plus Q. If Q is like X comma Y, then the way we define tangent and chord method, okay, so we define the operation, we can able to compute what is the X coordinate and Y coordinate of P. If we compute the X coordinate of P, this X coordinate will look like this. X coordinate is nothing but X square plus N square by 2Y power whole square. Okay, it's a perfect square in rational, because little x and little y are rational numbers, and the denominator is really divisible by 2. Okay, so the following theorem really characterizes the points inside this. What is the theorem? It says, let P be a point inside P be a point which is non-identity point if the point inside this particular subgroup, if and only if the X coordinate satisfying the relation, the X coordinate satisfies this following condition: X naught minus N, X naught plus N, all are squares of rational numbers. Okay, we are not proving this, but you can get a proof in one of the article or one book is there. Okay, so this is really characterizing what this subgroup captures really. Okay, so therefore the first observation, what is the first observation? Let us go back. First observation says, you see, already we have found out right angle triangle whose area is N, and the correspondence, okay, X, rational number X, correspondence between rational number X and the right angle triangle whose area is N, this way. Okay, so with this and this particular subgroup, this characterization with first observation 1 and 3, we can get the following thing. There is a one-to-one correspondence between right angle triangle with sides X, Y, Z, and the area is N, and pairs the points X comma plus minus Y inside the subgroup which is not identity. Okay, so the correspondence is given like this. It is coming from that same observation 1 and the characterization of the subgroup. Okay, now we can reformulate Martin-Gardiner's problem. Okay, how? You see, before going into, I will recall. So if we want to solve Martin-Gardiner's problem, we have to construct a 3 AP among squares. Okay, 3 AP among squares we have to construct. Okay, you here any point of this subgroup gives rise to one particular, the x coordinate gives rise to arithmetic progression among squares. Therefore, we have to find 3 distinct points in this particular subgroup. That's all it says. Okay, prove or disprove there exist 3 integral points P1, P2, P3 belongs to this subgroup, which are non-identity for some n, such that their x coordinates are in arithmetic progression. Why their x coordinates are in arithmetic progression is needed? Just because of to construct the magic square. Once again, I will go back and show why it is really. Once again. Okay, so here 3, you look at the top, the magic square is same as constructing 3 arithmetic progression with same common difference, row wise as well as column wise also it is arithmetic progression. Therefore, if x0 is there, x0 p1, x0 p2, x0 p3 is there, then these 3 first column should be in arithmetic progression. Once first column is arithmetic progression, second column, third column will be automatically arithmetic progression. Okay, so therefore, once, okay, now because of this observation, we can finally end up in, one second. Okay, finally we end up in this particular group. So Martin Gardner's problem is really equivalent to saying that to prove or disprove there exist 3 integral points. Integral points means with integer coefficient. Okay, p1, p2, p3 inside this subgroup for some integer n, such that the each of the x coordinates of p1, p2, p3 should be in arithmetic progression. Once these 3 points are inside this particular subgroup, then the previous observation takes care of. It gives you really this, whatever first one is x1, x2, x3 is the x coordinates. x1 minus n, x1 plus n, all 3 are perfect squares, and it forms an arithmetic progression already. Okay, all 3 are perfect squares. So therefore, once you say that x1, x2, x3 are in arithmetic progression, then it takes care of completely that magic square. Okay, the distinct will come just because all these points are distinct, that automatically puts into distinct. Okay, so distinct, it's enough to prove. If we want to really prove the existence of 3 by 3 magic squares of squares whose entries are all distinct, it is enough to prove this particular problem in the elliptic curve side. Okay, so therefore the study of congruent number elliptic curve is linked with the magic square of squares in this way. Okay, in 2000, Brumner, Silliman, and Zanakis proved that what they proved, given n bigger than 1 be a square free integer, n is a square free integer, and look at the elliptic curve, congruent number elliptic curve, and take any subgroup of rank 1. Any subgroup of rank 1 here means any subgroup kind of isomorphic to Z. This is like isomorphic to Z, cyclic group. Okay, so once a subgroup of rank 1, then that subgroup does not contain any non-trivial integral arithmetic progressions. So this theorem really says in our setup, we have to look for n such that the rank of En should be more than 1. In fact, we are looking for n such that the rank of 2En is more than 1. If it is rank 1, 2En is rank 1, then by this theorem it doesn't contain arithmetic progression, integral arithmetic progression. Therefore, we cannot appeal to our deduction. Okay, so okay, therefore this is the hurdle. Beyond that, people have not progressed. Okay, So one recent, okay, I'll come back to this example again. One recent result in 2019. So what Brumner looked at it is a subgroup of rank 1. These people have looked at a subgroup of rank 2 in some sense. En is a congruent number elliptic curve of rank 2. Suppose if P1, P2, PD are the integral points in arithmetic progression in x coordinates, then the D has to be at most 13. Okay, these are all kind of conditions they need in order to force D is 13. Here H is a height will come. These are all x coordinates. These are all integers. Okay. This x coordinate should be more than little n, etc. These are all kind of mild conditions. This condition implies that if rank 2 elliptic curve contains arithmetic progression among integral points, then the length cannot be more than 13. That's what recent result says. Okay. So other than these two results, general result, nobody knows exactly how one progress in that problem. So there are in 1997, one person cooked up a magic square. It is not really magic except one particular counter diagonal. Rest all it's some column, everything is magic, and diagonal also magic, but not the counter diagonal. Okay, it is not magic only, it fails to be magic only counter diagonal. So Andrew Brumner, in 2 years later, Andrew Brumner parameterized this particular example, how one kind of recently also there are papers. This is called semi-magic squares. Okay, kind of semi-magic square and elliptic curves. They have given another link. They are studying this particular type, but the point is, main problem still remains open. Nothing is known. My main reference of this talk is a paper of Robertson in 96, I guess, and another nice article of Conrad on arithmetic progressions of 3 squares. Other elliptic curves reference is Neil Koblitz on Introduction to Elliptic Curves and Model Forms. Okay, there are when we come, there are many natural question arises. What are the question? Can there exist arbitrary long arithmetic progressions on a rational points on elliptic curve? Because we have seen that, okay, if it is of rank 2, then D cannot be more than 13. Okay, many have worked on this particular problem, but I am not getting into. Just one naturally ask the question in the elliptic curve side. Many authors explode on this problem, but interested readers can check the literature. Okay, references. This Conrad article is online. One can take that, and he has given all the whatever I have stated. He has given a proof. One can check that. So arithmetic progression among 3 squares. Okay. So the other Robertson is 1996 magic squares of squares. Here only he gives 3. Gardner's problem is equivalent to elliptic curves problem, equivalent to the triangle's same triangle problem. Okay, so he gives the equivalence of that problem here only, and I have kind of expanded that Robertson article. Okay, this is the end of my talk. Hello.
Thank you very much. Thank you very much, Professor, for giving us a detailed lecture about the magic squares. I thank you for choosing this topic because apart from interesting the mathematics students, it will also kindle the interest of general public since magic squares and Sudoku puzzles are part of recreational mathematics. So I thank you for that. So now I request the students to raise any questions they have for our professor so that our professor can answer the questions and we can benefit from them. So students, please go ahead and type your questions in the comment box, please.
Vijay Kumar, is there any questions?
there is no question, sir. We'll see in a few minutes.
Can I see the participant list? No, no?
Dear students, I request you to use this opportunity to raise your questions and get it answered from our professor.
Sir, the magic square with semi magic square construction has been established in the paper that you mentioned.
Some paper is there. I can send you the reference. I have
Okay.
seen
Now that has been constructed actually.
the whatever I have said, that parameterization has been done. Maybe that they have. I have not seen that paper. Semi
Okay.
square and elliptic curves. The title of the paper is. It's I guess American Math Monthly. I guess.
Okay. Have they have anyone tried about more than 3 by 3, sir? Or how about the case for general case like 4 by 4? Or I think
Mm,
because the construction of magic squares have different rules according to their orders.
yeah, obviously, yeah. But of course, this kind of theory side will not get into because that is in surface, different curve.
I
So
think if
there
you take higher order magic square, the complexity of calculation will increase. If I feel.
increase, yeah, that is of course is there.
Okay, so any questions from students? Vijay Kumar, please.
Still, there is no question, sir.
Or any other teachers who attend this? Any other teacher? Okay, if there are no questions, I think we can go for Kalyan Kumar. Please ask Madam to propose vote of
Yes,
thanks.
yes, sir, sure, sir.
You can
So,
share my, you can
Sir,
share
if
my,
you want to say few words, you can mention.
yeah, okay,
And
okay,
we have released our e-magazine, sir. Our association has released e-magazine containing expository articles. We are going
okay,
to do 2 issues per year.
oh, okay,
So beginning from this year, we have released yesterday. I will send a copy to you.
sure,
okay, so now I request Miss. Now I request Miss J. Sugandhi from Pi Mathematics Association to deliver vote of thanks to our distinguished speaker.
Yes, my voice is audible.
yes,
Yep.
Yes. Good morning, everyone. I'm Sukanti. On this wonderful morning, I'm here to present a vote of thanks. On behalf of Pi Mathematics Association, I would like to extend my heartiest thanks to
Yeah,
our
yeah, you can
Honorable
proceed,
Chief
madam.
Guest.
Yeah,
Yeah,
it's audible.
yes. Yes, yes, okay. On behalf of Pi Mathematics Association, I would like to extend my heartiest thanks to our Honorable Chief Guest, Professor R. Thangadurai, for visiting and enlightening us with their knowledge. Sir, today's lecture was quite interesting, sir. It gives knowledge, innovative ideas, and more informative, sir. The point where you told us about the magic square in connection with the arithmetic progression is really superb. And then connection with the congruence numbers, elliptic curves with cubic equations are very quite interesting, sir. And one more thing I want to share this on Ramanujan Remembrance Day. In Ramanujan notebook, the first chapter was written about two 3 by 3 magic squares. So the topic that you have chosen today is very apt, sir. We are very happy to share this information to you. Thank you very much, sir. And then you're an exemplary person, and we have a lot to learn from you. Once again, thank you very much, Professor. And next, I would like to thank our PI Association members for your hard work, which has made this function a memorable one for all of us. And then a special thanks to goes to Professor R. Sivaraman, founder of Pi Mathematics Association, who gives moral support to all. Thank you, sir. And thank you everyone once again for making it a great success. Have a good day. Thank you.
thank you.